Hello dear students, welcome to mathematics class. In this class, let us discuss the theorem. So here it is a statement of the theorem. If f belongs to R of closed interval a b and there exists a value c in between a and b such that a less than c and c less than b, then f belongs to R of closed interval AC, means f is Riemann integrable on the interval AC and also f is Riemann integrable on the interval CB, and also we need to prove that integration over a to b f of x dx is equal to integration over a to c f of x dx plus integration over c to b f of x dx, because here we are dividing the interval a b into two sub intervals from the first point a to c, then from c to b, and union of those two intervals is equal to the given interval a b. So here it is given that f is Riemann integrable on the closed interval a b, then there exists a point in between a and b, then we need to prove that f is Riemann integrable on the interval ac and f is Riemann integrable on the interval cb, and then the Riemann integral integration over a to b f of x dx is equal to integration over a to c f of x dx plus integration over c to b f of x dx. Now let us prove this one. So given that f belongs to R of closed interval AB, means f is Riemann integrable on the closed interval AB. So if f is Riemann integrable, then we can say that f is a bounded function. So therefore it implies that f is bounded on the closed interval AB. So here, since f is bounded on the closed interval AB, then we can say that f is bounded on the two subintervals AC to CB. So therefore it implies that f is bounded on the interval AC as well as on the interval CB. So therefore here f is bounded on the interval AB, and then we can write f is bounded on the intervals AC and CB here, because a less than c less than b, means c is the point in between a and b. Now since f belongs to R of closed interval AB, for given epsilon greater than 0, there exists a partition P of closed interval AB such that UPF minus LPF is less than epsilon. So here it is the necessary and sufficient condition for a function f to be Riemann integrable. So here it is given that f is already a Riemann integrable function. So therefore since f is Riemann integrable, then we have to write the condition that UPF minus LPF is less than epsilon, where epsilon is a arbitrary constant which is greater than 0. Let P dash. Now let us consider one more partition, that is P dash. So P dash is equal to P union the point C. So here P is the partition on the closed interval AB. Now let us introduce the one more point C, and now take the union of the previous partition, that is P, and the new point C, then union of these two will be the new partition, that is P dash. Then we can write that LPF less than or equal to LP dash F less than or equal to UP dash F less than or equal to UPF. So it is because P dash is the refinement of P, because P dash contain one extra point, that is C. So therefore P dash is the greater partition. So, hence it is the refinement of P. So, here the reason is P dash is refinement of P. So, by considering this inequality, we can write that U P dash F minus L P dash F is less than or equal to U P F minus L P F, which is less than epsilon, and consider this as the first equation. So, here by considering this inequality, that is L P F less than or equal to L P dash F less than or equal to U P dash F less than or equal to U P F. So, here by shifting this L P dash to U P dash F, that becomes a negative. So, therefore, U P dash F minus L P dash F less than or equal to, now shifting this L P F to the last, this becomes the negative. So, therefore, U P F minus L P F, and it is given that U P F minus L P F is less than epsilon, since F is Riemann integrable function. Let P1 comma P2 denote the set of points of P dash on the closed interval AC, the closed interval CB respectively. So, let us consider the two set of points P1 and P2, where P1 is the set of points on the interval AC and P2 is the set of points on the interval CB. So, now it implies that P1 comma P2 are the partitions on the closed interval AC and the closed interval CB respectively. So, therefore, P dash can be written as P1 union P2. So, that is the common refinement of P1 and P2, and which is greater than both of them, because P dash is the union of two partitions, hence it is greater than P1 as well as P2. So, therefore, we can write that U P dash F can be written as U P1 F plus U P2 F. So, here upper Riemann sum of the function on the partition P dash is equal to sum of the two upper Riemann sums of the function F on the partition P1 and P2. Since P dash is the union of P1 and P2, so therefore, its upper sum can be written as U P1 F plus U P2 F. Similarly, the lower Riemann sum L P dash F. So, this also can be written as L P1 F plus L P2 F. So, here lower Riemann sum of the function F on the partition P dash is equal to L P1 F plus L P2 F, means lower Riemann sum of the function F on the partition P1 plus the same lower Riemann sum of the function F on the partition P2. So, this is because P dash equal to P1 union P2. Union means we need to add the partitions. Now, this is equal to, now subtracting this one, it is U P1 F minus L P1 F plus U P2 F minus L P2 F. So, here subtracting these two equations, and this is equal to U P dash F minus L P dash F, which is less than epsilon. So, it is from equation 1. So, in equation 1 we have U P dash F minus L P dash F is less than epsilon. So, therefore, now here we have subtracted these two equations. Now, U P1 F minus L P1 F plus U P2 F minus L P2 F is equal to here it is u p dash f minus L p dash f, and this one is less than epsilon from equation 1. Now, since each of u p1 f minus L p1 f and u p2 f minus L p2 f is non-negative, because we know that upper Riemann sum is always greater than lower Riemann sum of independent of the partitions. So, therefore, here upper Riemann sum of the function f on the partition P1 will be greater than lower Riemann sum of the function f on P1. So, therefore, its difference is always greater than or equal to 0, and similarly u p2 f minus L p2 f is also greater than or equal to 0. Hence, they are non-negative, and each of them is less than epsilon. So, that is u p1 f minus L p1 f is less than epsilon, and u p2 f minus L p2 f is less than epsilon. So, therefore, now here P1 is the partition on the closed interval AC and P2 is the partition on the closed interval CB. So, therefore, here P1 and P2 are partitions of the closed interval AC and the closed interval CB respectively. So, therefore, by using the necessary and sufficient condition for Riemann integrability, we can say that u p1 f minus L p1 f is less than epsilon. It means that f is Riemann integrable on the partition P1, and P1 is the partition of the closed interval AC. So, therefore, now since u p1 f minus L p1 f, u p1 f minus L p1 f is less than epsilon. So, therefore, it implies that f is Riemann integrable on the interval AC. So, here because if u p f minus L p f is less than epsilon, it implies that f belongs to R of closed interval AB, where that P is the partition of the closed interval AB. But here P1 is the partition of AC, hence the function f is Riemann integrable on the closed interval AC, and that is u p2 f minus L p2 f is less than epsilon. So, it implies f belongs to R of closed interval CB, because this P2 is the partition of the closed interval CB. Hence, that f is the Riemann integrable over the closed interval CB. Now, u p dash f, this can be written as u p1 f plus u p2 f. Now, one part is completed, that we have proved that f is Riemann integrable on two subintervals, that AC and CB, and then we need to prove that the one more result, that is integration over a to b f of x dx is equal to integration over a to c f of x dx plus integration over c to b f of x dx. So, u p dash f is u p1 f plus u p2 f, since because p dash is p1 union p2. Now, considering the infimum of u p dash f and infimum of u p1 f plus infimum of u p2 f. So, here you have considered infimum of all the three upper sums. Now, infimum of upper sum is nothing but upper Riemann integral, that is integration over a to b bar f of x dx is equal to, and now here P1 is the partition on the closed interval AC. So, therefore, it is integration over a to c bar f of x dx plus P2 is the partition of the closed interval CB. So, therefore, it is integration over c to b bar f of x dx. Now, we know that here we know that f belongs to R of closed interval AB, means f is Riemann integrable on the closed interval AB, and also we have proved that f belongs to R of closed interval AC, means on the closed interval AC f is Riemann integrable, and one more point is f belongs to R of closed interval CB. So, means on all these three intervals f is Riemann integrable. So, Riemann integrable means upper Riemann integral is equal to lower Riemann integral is equal to the common value of the Riemann integral, that is integration over a to b f of x dx, or here we can write that integration over a to b bar f of x dx is equal to integration over bar a to b f of x dx is equal to integration over a to b f of x dx. So, this is also a condition for Riemann integral, means if the function is Riemann integral, then upper Riemann integral is equal to lower Riemann integral is equal to Riemann integral, that is the common value of these two. So, therefore, here in the first one the function is defined on the closed interval AB. So, therefore, f is Riemann integrable on the closed interval AB, then we can replace this as the common value of the Riemann integral, that is integration over a to b f of x dx, and on the second term f is defined on the closed interval AC, hence we can replace that upper Riemann integral as integration over a to c f of x dx, and here integration over c to b f of x dx. This we have written because f is Riemann integral on the respective intervals, otherwise we cannot write this as integration over c to b or a to c or a to b. So, therefore, the result is integration over a to b f of x dx is equal to integration over a to c f of x dx plus integration over c to b f of x dx, hence the result. So, here we have proved that if C is the point in the closed interval AB satisfying the condition that A less than C less than B, if this condition is satisfied, then we can say that f is Riemann integrable on the interval AC, then on the interval CB, that we have proved, and also this one integration over a to b f of x dx equal to integration over a to c f of x dx plus integration over c to b f of x dx. So, hence the theorem proved. The next theorem is, if f belongs to R of closed interval AB and f of x is greater than or equal to 0 for all x belongs to the closed interval AB, then integration over a to b f of x dx is greater than or equal to 0. So, here if f is a Riemann integrable function and f is positive for all the values of x in the interval AB, then we need to show that the Riemann integral, that is integration over a to b f of x dx is also positive. Now, the proof: given that f belongs to R of closed interval AB, means f is Riemann integrable on the closed interval AB. Since f is Riemann integrable, then it implies that f is bounded on the same interval AB. Since f is bounded, then there must exist infimum as well as supremum for the function f. So, therefore, let small m and capital M be the infimum and supremum. of the function f on the closed interval a b. Since f of x greater than or equal to 0, it is given f of x is always positive for all the values of x in the interval a b. For all x belongs to closed interval a b, then it implies that its infimum is also greater than or equal to 0, because infimum means that is also the value of the function f for some value of x, is it right? So, therefore, if f of x is greater than or equal to 0 for all the values of x, then its infimum and supremum both must be greater than or equal to 0. Here we have considered the infimum, that small m is always greater than or equal to 0. Now, for all partitions of P, for all partitions P of the closed interval a b, we have LPF, lower Riemann sum, is always greater than or equal to small m into b minus a greater than or equal to 0. Now, here we know the result that small m into b minus a is less than LPF, right. So, here we have written the same result in the reverse order, that is LPF is greater than small m into b minus a. Here, since m is greater than or equal to 0 and b minus a is always positive, so therefore, this product is always greater than or equal to 0, then it implies that each LPF is always greater than or equal to 0, means all the lower Riemann sum of the function f over the partition P will be greater than or equal to 0. Now, let us consider lower Riemann integral bar a to b f of x dx. Lower Riemann integral is nothing but supremum of LPF, where P is the partition of the closed interval a b. P belongs to P of closed interval a b. Now, here by the definition of lower Riemann integral, that is bar a to b f of x dx is equal to supremum of all the lower sums. So, here we got the result as LPF is greater than or equal to 0 for all the values of x. So, means here each LPF is greater than or equal to 0, then indirectly the supremum of LPF must be greater than or equal to 0, because each LPF is greater than 0, then it implies that the supremum of each LPF or all the LPF must be greater than or equal to 0. So, therefore, it can write as integration over bar a to b f of x dx is greater than or equal to 0, because bar a to b f of x dx is nothing but supremum of LPF, and supremum of LPF is always positive, means the integral bar a to b f of x dx must be greater than or equal to 0. Then we can write this as integration over integration over a to b f of x dx is greater than 0, because f is a Riemann integrable function on the closed interval a b. If f is the Riemann integrable function, then lower Riemann integral and upper Riemann integral both are same, and they are equal to the common integral, that is integration over a to b f of x dx, and it is always greater than or equal to 0 if the function is positive for all the values of x. So, therefore, this is the theorem. If f is positive, then the Riemann integral of that function on the interval a b is also positive.